Just a little side note before we get going here. We're having some issues with our content transmission. So if my computer screen disappears on you at any time, please don't be afraid to yell out and let me know. It's been cutting out like every 6 or 7 minutes here today. So we know it's an issue and we're working on it. So just give me a yell if it disappears on us. I'll try to make sure I notice it if it goes. Okay, so for this problem, we're looking at how much pure alcohol should you mix with 120 milliliters of a 30% alcohol solution to create a 58% solution. So the first step is to look at what we're mixing. Obviously, we have a 30% solution, but we're mixing with it pure alcohol, which of course is a 100% solution, or pure. And we're going to create that 58% solution. So we need to look at our volumes or our amounts. The only amount we're given is the 120 milliliters of that 30% solution. So 120 milliliters of that. We're looking for how much pure alcohol. So X will let be the amount of the 100%, the pure alcohol. So the amount for the 58% solution, we just add those together, 120 plus X. So now we'll create our equation. For the 30%, it's concentration times volume. So 30% is 0.3 times 120 milliliters. For the pure alcohol, concentration times volume, 100% is just 1 times the volume of X equals, for our 58% that we're trying to create, concentration is 0.58 times the volume is 120 plus X. So now remember our steps for solving equations. We always simplify what's on each side first. So on the left side, I can do 0.3 times 120 is 36. 1 times X is just going to be X. So that's all I can combine on the left side. On the right side, we have the parentheses. We should do something there first. We're going to multiply through by the 0.58. So 0.58 times 120 gives us 69.6. And 0.58 times X is 0.58X. So we've combined everything that we can on the right side of the equation as well. Now remember, the next step is to make sure the variable only appears on one side of the equation, only appears once. And here it appears twice, so we have to get rid of 1. The 0.58 is the smaller one, so we will get rid of that by subtracting it. We have to subtract 0.58 from the X on the other side. Remember that X gets treated as just a 1X. So now we have 36 plus 1 minus 0.58 is 0.42X equals 69.6. Now we're at that point where we can solve the equation. So we're taking it apart. Subtracting the 36. 0.42X equals 69.6 minus 36 is going to be 33.6. And finally, we divide by the 0.42. So X equals 33.6 divided by 0.42 gives us 80. So now we have to go back and make sure we know what X stands for and be sure that it answers our question. X, which we got to be 80 milliliters, is the amount of the 100% or pure alcohol. And we are asked to find how much pure alcohol. So 80 milliliters is our answer for that question. Does anybody have any questions on those mixture problems? Okay. Well, today then we're going to move on to what I view to be the most powerful concept in math. We've actually done a form of it already in Unit 1, and we'll review that a little bit as well if we have some time today. But it's the most versatile and powerful tool in math because it really is the basis for many of our more advanced applications like trig and dimensional analysis and stuff like that. And that is the concept of a ratio. A ratio is nothing more than a comparison between two numbers. So, for example, I might compare the number of students that are in my network math for health professionals class to the number of students who are in my classroom class. We have 18 students over the network this semester, and I have currently 21 students in the classroom. One way to express that ratio is just like I did there in a fraction form, but there are other ways to do it. I can do it as 18 colon 21, or I have to be careful with this one, 18 to 21 would be appropriate in this case. Any of those forms would be appropriate. Now, I prefer to write it as a fraction like this because there's a lot of things I can do with a ratio that are very similar to things I can do as a fraction. Both 18 and 21 can divide by 3. So I can reduce that ratio just like I would a fraction. 18 divided by 3 is 6. 21 divided by 3 is 7. To get that 6 to 7 ratio. Now I can reduce it in these other forms as well. You divide both the 18 and 21 by 3 to get 6 to 7. It's just we're used to doing it as a fraction. Now, something here with this form right here that we have to be careful of. There are two types of ratios that we will deal with. One type, which is what this one is, compares two pieces within a whole. So say two parts within a group. These are the only two classes that I have, so these actually make up the whole group. So it's a complete comparison, but I have network is part of my group of math for health professional students, and my in-classroom is the rest of my health professional students. Well, the second comparison that can be made is a part of a group to the whole group. So I could have, instead of saying comparing my network students to my in-class students, I could have said what ratio of my network students is to all of my students. And that would have been 18 on the network to 39. Notice that adds up. 18 plus 21 gives me the 39. That's my total. Now, that would be expressed the same way as a fraction or with a colon, but if I were to do it here, rather than saying 18 to 39, I would say 18 out of 39. So that second type of ratio has a little bit different wording that you use if you express it with words. But it can also still be reduced exactly the same as any of the others. Both of those are divisible by 3. That gives me a 6 out of 13, or 6 to 13 ratio. That process of working with ratios like that difference between comparing two parts within a group and comparing one part to the whole group, is huge when we do our dosage calculations in the next unit. A dilution is totally a ratio, but it's that second type of ratio where it's a part to the whole. And we need to be able to switch it from being a part of the whole to two different parts within that whole by switching that around. For example, let's go to my evening class. I have an evening business math class. And if I were to tell you that 8 out of 28 students earned an A on the last test? Well, 8 out of 28, I can write that as a fraction is a ratio, and I can reduce that. Both of those numbers being divisible by 4 gives me a 2 out of 7 ratio. But I could also then change it. Well, if I wanted to know what ratio, what proportion of the students did not receive an A or did not earn an A, I can just look at what's left over. I could either do 28 minus 8 gives me 20 out of the 28, and I could reduce that. Both numbers divisible by 4 gives me 5 out of 7. Or I could have just looked at this 2 out of 7 ratio after I'd reduced the first one. If 2 out of 7 got A's, the other 7 minus 2, or 5 out of 7, did not get A's. So we can work with our ratios in that manner. Let's look at another ratio. Looks like you guys have some similar tables around your room, but I have my tables in my classroom here. If I look at a length to width ratio, the length of my tables are 6 foot, so those are 72 inches, and they're 18 inches wide. So you can see the inches cancel out, and both 72 and 18 can actually be divided by 18. 72 divided by 18 is 4. 18 divided by 18 is 1, giving me a 4-to-1 ratio. Now, here is one of the places where this is different from a fraction. And if this were just a fraction, if I got it reduced where the denominator was 1, I could get rid of the fraction and just put a 4. But this is a ratio, and it must compare two numbers. So I have to have 4-to-1. This is actually something special called a unit ratio. And in a unit ratio, that bottom number, or the second number, is a 1, or 1 unit. In ratios, there are some ratios that we do usually express as unit ratios. But in the most case, we can leave them like we had up above, that 5-to-7 or 2-to-7. We reduce them as far as we can, and we leave them like that. One thing you may have noticed in the ratios so far is all of the things I have compared have been the same type of thing. They've had the same label. Here it was 72 inches to 18 inches. Up above, it was students to students. And that is one qualification of a ratio, is it must compare things with the same label or same unit. Oops, writing's a little sloppy there, but you get the picture. So if I have something like 2 feet to 18 inches, that is not a ratio as it's written. Now I can change that. We can convert 2 feet into 24 inches. So I've got 24 inches to 18 inches. That's now a ratio. And of course I can reduce it. The inches cancel. Both 24 and 18 can divide by 6 to give me 4/3. Now here's another big difference between our ratios and fractions. If this here were a fraction, since the top number is bigger than the bottom number, I would want to change it into a mixed number of 1 1/3. But since this is a ratio, we do not do that. We will never reduce it to a mixed number because that's not how a ratio works. A ratio, remember, is a comparison between the two numbers. Doesn't matter if the top one's bigger or smaller. We're comparing the numbers. Well, what if we have two numbers that don't have the same units? Let's say we decide we're going to go for a drive. We're going to go on a road trip. And we're going to drive 365 miles. And let's say it takes us 7 hours to make this drive. There is no way to convert miles into hours or hours into miles. It cannot be a ratio. We can't create it, turn it into a ratio. What is what we call a rate? So the first big difference between rates and ratios is that a rate can compare two things with different units, different labels, whereas that ratio had to have two things with the same unit, same label. The second big difference is in the ratio, it didn't bother us to leave it as 4:3 or 5:7. I mean, sometimes we converted it into that unit ratio like we did with the 4:1. It just happened to work out that way. But a rate is almost always converted into what we refer to as a unit rate. And a unit rate, just like the unit ratio, that second number becomes a 1 or a single unit. Now, it doesn't mean we have to get rid of the hours, we just have to get rid of the 7. So what we do is we divide by the numerical value in that second number. It's the 7. Now, just like with a fraction, I have to divide the other number by the same thing. So 7 hours divided by 7 is just 1 hour. 365 miles divided by 7 is 52.142857, I believe, miles. The bottom here is 1 hour. That is a single unit. So this is now a unit rate. Now, we would not usually leave it like this. First of all, I'd round this top number off probably to 1 or 2 decimal places. Let's say we're going to go to the nearest hundredth. So we'd make that 52.14. And instead of writing it as miles over 1 hour, we would just write it as miles per hour like that. So you can see that appearance of the fraction is now hidden in the units. In fact, we often will go a step further. Rather than writing it as miles/hours, we might even do this, 52.14 mph, where the appearance of the fraction is gone completely. But you have to remember it is still there. Let's say that on this trip, we got 24 mpg. mpg, of course, stands for miles per gallon. So 24 mpg, whenever we see that, we need to think this. 24 miles per 1 gallon. Because this is the form we need it in order to do any calculations with it or to work with it. Well, let's look at some other rates that we have out there. Miles per hour, miles per gallon. Other rates that you guys might be familiar with might look something like this. You might get paid $45 for a 5-hour shift. Convert that to a unit rate. We would divide by that denominator, the 5, gives us $9 per 1 hour. Of course, rate that is $9 per hour. We leave the 1 out. That's your wage. You might have in the medical fields, important rates. Might be flow rates. If we infuse 1,200 milliliters of fluid over 3 hours, that's going to give us a flow rate 1,200 milliliters over 3 hours, and we convert that into a unit rate by dividing by that bottom number of 3, which is 400 milliliters per 1 hour. Or, of course, just 400 milliliters per hour. We also have drop rates. We might have Oh, let's see here. Let's say we have 4 milliliters of fluid containing 48 drops. A drop factor is the rate of drops per milliliter. And we've mentioned before, a lot of times the units can tell us how to figure this out. If a drop factor has units of drops per milliliter, that means it's going to be drops on top of our ratio or rate and milliliters on bottom, because we have to make the units line up just like they are in the units of the final result. So we can divide by 4. 4 milliliters divided by 4, of course, is just 1 milliliter. 48 drops divided by 4 is 12 drops. Now, the abbreviation we use for drops in the medical field is GTT. So this would actually be written most likely as 12 GTT for drops per milliliter, like that. So that'd be the drop factor, or the drop rate on that fluid. It's actually a property of the fluid. The thicker the fluid is, the lower the drop factor is, because it takes fewer drops to make 1 milliliter. Let's look at some ratios. Ratios, of course, are everywhere. We looked at just comparing students to students or length to width. There are all sorts of mechanical ratios out there that you can run into. In mechanics, you might have gear ratios. Where you'll have, this is going to be kind of ugly, but pretend that looks like a gear. Where you have the number of teeth. We have 12 teeth on the big gear and 8 teeth on the little gear. A gear ratio usually goes what's called driven over driving. Whichever one is connected to the power source goes on bottom. So if we imagine that that is a small motor connected to the larger gear, this is actually 8 teeth to 12 teeth. Because the one connected to the power source, the 12 teeth, goes second or on bottom. So the teeth cancel out. Both of those numbers divide by 4, giving us a 2 to 3 gear ratio. And that gear ratio, of course, will be the ratio of teeth, but it's also the ratio of RPM and the ratio of torques and other things within those gears. In the medical fields, we'll have all sorts of ratios of medicine, mixture ratios. We might have 40 milliliters of medicine. Now, remember, the term we're going to use for generic medication is the term serum. So that just refers to any sort of medication. So 40 milliliters of a serum in, that's just our notice from Hurley, there's no way there. So we have 40 milliliters of serum in 200 milliliters of, and remember, NS is our abbreviation for neutral solution or normal saline. So we've put 40 milliliters of serum into 200 milliliters of saline. So the ratio of serum to saline, NS, is 40 milliliters over 200 milliliters. And so the milliliters can cancel out. Now you might ask, since the units always cancel out in a ratio, is it important to put them in there? It isn't important. You don't have to have them there because our result will always be unitless. But just make sure that the two numbers you're using do have the same units. Now, of course, 40 and 200 both divide by 40, creating a 1 to 5 ratio. Now, we just mentioned those units divide out, so the units really don't matter. And that's true even from the ratio. I can have that same mixture of serum to saline if this is 1 fluid ounce to 5 fluid ounces. It would give me the same ratio as if it was 1 milliliter to 5 milliliters. Or it could be 1 pint to 5 pints, or 1 grain to 5 grains, or whatever unit of measurement we want to use there can be used as long as we use the same unit for both. Because the actual units within the original measurements cancel out, it no longer matters. A ratio that could be important to all of you hopefully at some point in your life is something called a debt to income ratio. You hear a lot of stuff on advertisements on radio and television, whatever, about credit scores. And credit scores are very important, but when you go to get a loan, it's not necessarily your credit score that determines if you get that loan or not. If you have a terrible credit score, that could stop you from getting the loan. But most of the time, the credit score, the better your credit score is, the lower interest rate you're going to get. So that credit score determines whether you get a low interest rate or whether you have to pay a high interest rate. But whether you get the loan or not depends on a debt to income ratio. That basically is how much of your income is already tied up in debts. For example, let's say you have a car payment of $200 a month. Let's give you credit cards of $100 a month and a mortgage. Actually, let's not do a mortgage. Let's do a personal loan. Let's say you have like a four-wheeler or motorcycle or something like that. We're just going to list it as personal. That is $200 a month as well. That gives you total debt payments of $500. Notice this does not include food or gas or anything like that. Those are not debt payments. These are dedicated debt payments that are paid every month. Your income. Well, let's say that your income is $2,500 a month. You have a $30,000 a year job. Your debt to income ratio, you have $500 in debt to $2,500 in income. Both of those divide by 500. You can get a 1 to 5 debt to income ratio. That's actually a pretty good debt to income ratio. Depending on your bank, most of them want it to be a 1 to 3. Some will push it up to a 2 out of 5. That's just saying, again, what fraction, what portion of your income is already dedicated to debt payments. So here you have room, a 1 to 5, 1 out of 5, only $1 for every $5 you make goes to debts. You have room to borrow more money for other things if you're looking to buy a home or something else, and you would still stay under, hopefully, that 1 to 3 desired ratio. So what do we do with these ratios? Well, let's see that you have that ratio, that you need to mix that serum into a saline, to create a solution. And let's say it's going to be 2 units of serum for every 5 units of saline. And you need to use, the patient needs 24 milliliters of medication, of the serum. We need to know how much has to go here. Well, there are a couple of ways to look at this. And we can look at this as equivalent fractions where we multiply the top number and the bottom number by the same thing. To turn the 2 into a 24, it was multiplied by 12. So 5 times 12 gives us 60. So we would mix that 24 milliliters of serum of medication into 60 milliliters of that sterile water. We also saw, when we did percents in Unit 1, that when we have two fractions, or in this case, two ratios that are equal to each other, we can find that missing number using a shortcut. And that shortcut was cross multiplying. Now, we did actually a shortcut of that shortcut. I'm going to show you the long process. What cross multiplying says is when I have two fractions that are equal to each other, I have a missing number in that one. If those two fractions truly are equal, in this case, two ratios is fractions, the cross products will also be equal. So the cross products are multiplying the two numbers that are diagonal to each other. 5 times 24 milliliters is 120 milliliters. Going this way, 2 times x is 2x. And those cross products have to be equal. So 2x has to equal 120 milliliters. So we solve that by dividing by the 2. X equals 60 milliliters. But as we saw with our percents, most of the time we end up with a simple equation like this. So we're just going to have to divide by one number to get x by itself. The number we divide by is going to be this one here, this diagonal with our x. So rather than cross multiplying and creating the equation, we cross multiply and divide. We multiply the two numbers that are diagonal, the 5 times 24 makes 120, and we divide by the number that's diagonal to our missing number. So just divide by the 2 to get that x equals 60. So we might have a flow rate of 200 milliliters per minute. Now this is a rate, not a ratio, but a rate can be used in one of these proportions as well. Oops, I don't want 200 milliliters per minute, I want 200 milliliters per hour. 200 milliliters per minute would be a lot of fluid. 200 milliliters per hour is our flow rate. And I want to know how much would flow in 6 hours. So again, we can just cross multiply and divide. 200 milliliters times 6 hours is 1,200. Now, if we're worried about the units, that would be milliliters times hours. That unit doesn't make much sense, but it is there. Now we're dividing by the 1 hour. So that cancels out the hours. 1,200 divided by 1 is 1,200. The units left are milliliters. Now, most of the time when I do these, I don't put the units into my calculation like this. I just know that this has to be the same units as this one. Those both have to be milliliters. So I know the units are milliliters, so I don't work with them. But working with the units like this, milliliters times hours is milliliter hours, and dividing out the hours to get milliliters is one way to make sure you're doing the calculation correctly. In many cases, if the units work out, the numbers should work out as well. That is something called dimensional analysis. And that is a tool we're going to use a lot in the next unit for our dosage calculations. We're going to use dimensional analysis basically to tell us how to do the conversions we need to calculate our dosages. The units actually kind of guide the whole process. So there we can cross multiply and divide, but it doesn't always stay that simple. Often we have things like this. X plus 3 over 21 equals 12 over 63. Here, we can't just cross multiply and divide because our missing number isn't by itself. It isn't just x here, it's x plus 3. There are a couple of ways we could go about this, but the simplest is probably to just cross multiply. So going in this direction, we have 21 times 12, which is 252, I believe. And going this way, it's easier for me to put the number first. We have 63 times x plus 3. And we can write that into an equation. 63 times the x plus 3 has to equal 252. So now we can go ahead and multiply 63 times x, 63x. 63 times 3 is 189, equals 252. Our next step to solve, I'll go through this kind of quickly because I know you guys can solve equations. We subtract the 189, so 63x equals 63, and of course we divide. Dividing both sides by 63 gives us x equals 1. Or you can run into proportions like this. 50 over 95 equals 5x over 19. So again, the variable, the number we're looking for, isn't by itself in this proportion. So we will just cross multiply. 50 times 19 is 950. 95 times 5x, 95 times 5x. So we have 95 times 5x is 950. We have to combine 95 times 5x is 475x equals 950. And of course we divide by the 475. We get x equals 2. I know I kind of rushed through those last examples because we're a little short on time. I'm going to slow down a bit on this next one. We might have something like 3x plus 1 over 30 equals 2x minus 1 over 15. Now here again, we're going to cross multiply. Doesn't matter which direction we go first. I'll go this way, going down. 3x plus 1 times 15, that is 15 times 3x plus 1. Going the other way, 30 times 2x minus 1. Again, that's 30 times the 2x minus 1. And we know those two have to be equal. Now again, we go through our process of solving equations. We know we simplify each side first. On the left side, we multiply by the 30 through the parentheses. 30 times 2x is 60x. 30 times negative 1 is a negative 30. There's nothing more to combine on the left side. So we go to the right side. We multiply the 15 through the parentheses. 15 times 3x is 45x. 15 times 1 is a positive 15. Now we have an x on both sides. We get rid of 1. We subtract the smaller one, the 45x. So 15x minus 30 equals 15. And from here, I know you guys can solve it, so I'll kind of cruise through it. You add 30. 15x equals 45, and divide by 15. Get x equals 3. Well, that's pretty close to all the time we have for today. So I'm going to give you some homework here. Our homework comes out of the book on page 73. Problems 1 through 39, the odds. These are going to be on writing the ratios and reducing them, and then also on finding missing numbers in proportion. Like I said, take the time on these because really ratio and proportion is the basis of most of the calculations we do in math. In trig, in dimensional analysis, even in what we did in percents. Percents are all ratios. We'll actually take a little bit of time on Wednesday to talk about percents again before we move on to some of our other stuff. But 80 to 90% of math is about ratios. So take your time on these. Anybody have any questions? Okay, well, you guys have a great day, and we'll see you on Wednesday. Thank you.